Welcome to Tungal Online Classes. Today we are going to discuss about the topic of moving coil galvanometer. Moving coil galvanometer. It's a very important question for the board as well as JEE point of view or NEET point of view. So here, what is the moving coil galvanometer and what is the need to consider the moving coil galvanometer? So the moving coil galvanometer is a device. The moving coil galvanometer is a device which can be used to measure, a small currents, very small currents that is in the order of 10 power minus 9 amperes. So what is the need of the moving coil galvanometer is by using the moving coil galvanometer, we have to measure a very small currents which are in the order of 10 power minus 9 ampere. For this purpose we are using the moving coil galvanometer. So here this moving coil galvanometer, how they will be asking the question means explain the principle, construction and working of the moving coil galvanometer. We have to explain what on which principle it is works and how the moving coil galvanometer will be constructed and how the working of the moving coil galvanometer will be existing. Like this we have to explain. So first one is what? We have to know the principle. The principle of the moving coil galvanometer is, it is working on the principle such that whenever the rectangular current carrying coil will be placed in the external magnetic field, over that coil some external torque will be acting due to the magnetic field. So this is what the principle of moving coil galvanometer. Once again, what is the principle of the moving coil galvanometer? Whenever the moving coil galvanometer will be placed in the external magnetic field, over it some external torque will be acts due to the external magnetic field. So this is about what? Principle of the moving coil galvanometer. And next one is what? Construction of the moving coil galvanometer. See, if you look at the diagram of the moving coil galvanometer is what we consider here. So in the principle what we told, whenever the loop is placed in the external magnetic field, some torque will be acting. So for that purpose, in the moving coil galvanometer, first one we consider a rectangular current carrying loop. What loop we consider here? Rectangular current carrying loop is considered. How the rectangular current carrying loop will be made? So first we have to consider a rectangular frame which is made with a non-conducting material. Over that non-conducting rectangular loop, we have to wind up a large number of turns of the insulated wire. So we have to take the rectangular frame, over that by using the insulating wire, we have to made so many number of turns. Such type of arrangement we are calling as rectangular loop. And this rectangular loop will be suspended between the magnetic poles with the help of phosphor branch wire. Especially which wire we used here? Phosphor branch wire. So by using the phosphor branch wire, this loop is suspended between the north pole as well as the south pole, and this phosphor branch will be suspended with the help of the rigid support, that is nothing but capital T, that is called what? Torsion head. From the torsion head, phosphor branch wire will be suspended. At the bottom end of the phosphor branch wire, we connected the rectangular current carrying loop. At the bottom of the rectangular current carrying loop, one more phosphor branch wire will be connected, and which is also connected to the helical spring. And if you look at the diagram, over the phosphor branch wire, a mirror will be placed placed. What is the use of the plane mirror in the case of the moving coil galvanometer? In the principle only we told. What we told? Whenever the loop is placed in the external magnetic field, over the loop some external torque will be acting. So whenever an external torque is acting on the loop, the loop will be rotates. So while the loop is making the revolutions, due to the external torque which is acting over it, so to find how many number of rotations made by the loop, how many number of rotations or revolutions made by the loop, for that purpose we are using the plane mirror. So what is the use of the plane mirror? Means while the torque is acting on the loop will be making the rotations. To count the number of rotations made by the loop, we are using what? Plane mirror. Next, this rectangular current carrying loop, whatever the rectangular current carrying loop, we consider that a rectangular current carrying loop is placed in between the two magnetic poles. Here, which type of magnetic poles we used here means concave shaped, horseshoe permanent magnets we use. Which type of magnets we used here? Concave shaped horseshoe permanent magnets we used. Out of all the magnets, the horseshoe magnets are producing the high intensive magnetic fields. For that purpose we use which type of magnets here? Horseshoe magnets. And moreover here we define a particular shape of the magnet. That is nothing but concave shape. Then what is the use of the concave shaped magnets? Means these concave shaped magnets are producing the radial magnetic field. These concave shaped magnets are producing which type of a magnetic field? Radial magnetic field. So what is the use, what is the need of radial magnetic field? Means by using the radial magnetic field, we will keep the plane of the coil, in the direction of the magnetic field. So what is the use of the radial magnetic field? The radial magnetic field is always keeping the plane of the rectangular loop in the direction of the magnetic field. Again, what is the use of placing the plane of the loop in the direction of the magnetic field? Means while the plane of the loop will be in the direction of the external magnetic field, the loop will be experiences the maximum external torque. So what is the need of this arrangement? Means here we have to get maximum torque. We have to get, for which purpose? For getting the maximum torque, all these arrangements we did. So we consider the radial magnetic field. For which purpose? For producing the maximum torque in the loop. For that purpose we consider the radial magnetic field. And moreover, one more portion we consider here, I. What is the I here means? I is indicating a soft iron cylinder. I is indicating what? Soft iron cylinder. Again, what is the use of the soft iron cylinder? Whenever you are placing any one of the magnetic material inside the loop, so it will attracting the many number of lines of forces through it. That means what? Over the loop, maximum magnetic field influence will be existing. What is the need of considering the iron cylinder? Means whenever the iron cylinder was placed within the loop, it will be attracting the many number of of lines of force which are passing or which are penetrating through the loop. Whenever so many number of magnetic field lines are passing through the loop, so maximum influence of the field will be presence over the loop. Hence we will get maximum field intensity is acting on the loop. Whenever the field intensity will be more, the torque also more. So all these arrangements what we did for getting the maximum torque only, like this we have to construct, the moving coil galvanometer. Now coming to the working. So when you consider the rectangular current carrying loop, when the torque will be acting on the loop, whenever current will be passing through the loop, already you know the formula for the torque. What is the formula for the torque? Tau is equal to BIAN. What? BIAN. So if there is no current is flowing through the loop, torque acting on the loop is equal to 0. When the torque will be acting, whenever the current is flowing through the loop, so that we have to switch on the power supply. As a result, current is flowing through the coil. Due to the external magnetic field, some external torque is acting on the loop. Due to the presence of the external radial magnetic field, torque will be acting on the loop when current is flowing through it. That external torque will be given by tau is equal to what? BIAN. Now, whenever some external torque is acting on any one of the rigid body, that rigid body will comes into the rotatory motion. Here which body we consider here? Current carrying loop is considered. So whenever some external torque is also acting on the loop, the loop will be rotates. So whenever the loop will be rotates, the loop will be getting some deflection. So that the deflection produced within the loop will be indicated by the theta. Once again, whenever the torque is acting on the loop, the loop will be bring into the rotatory motion, or the loop will be rotates. Whenever the loop will be rotates, it is making certain deflection, it is making some revolutions, so that some angular displacement will be takes place. So theta is indicating that the angle through which so the loop will be rotates. Now coming to the basic once again. Already we know about the simple pendulum concept. If the simple pendulum will be suspended like this, it is in the equilibrium position, means it is in the state of the rest. Whenever the pendulum will be displaced from its mean position, and if you release there, the pendulum will be coming to the mean position, and it is making what? Oscillations. So how that pendulum will be coming back towards the mean position means, when you remove the external force here, restoring force was developed within the bob. Once again, when you remove to displace the bob, to displace the simple pendulum, you must apply the external force. So at this position, if you remove the external force, the pendulum is coming towards the mean position, and it is making what? Oscillation. That means when you remove the external force, whenever the external force is absent, removed, switch off, at that time within the simple pendulum, restoring force is developed. Similarly here also, whatever the radial magnetic field we applied over the rectangular current carrying loop, as a result, the loop will be experiences the external torque. As a result, it rotates. Now, I am going to switch off the external magnetic field. I am going to switch off the external magnetic field. So whenever you switch off the external magnetic field, previously we discussed external force is removed, restoring force will be developed within the simple pendulum. So here we are removing the external magnetic field. We are removing the external magnetic field. As a result, what it develop means restoring couple will be develops. Restoring couple will be develops. What is the meaning of restoring couple? See here. If you take a simple pendulum, by applying the external force, external torque, you rotate maybe the pendulum in the anti-clockwise direction. If you remove the external torque, the bob will be rotates in the opposite direction. Whenever the external torque will be there, the rotation takes place in the anti-clockwise direction. When you remove the external torque, it will be rotating in the clockwise direction. That means in the absence of the external torque, the coil or the bob was rotating means, inside in it some restoring torque, restoring couple was developed. So that only we are saying that in the absence of the external magnetic field, the coil will be rotates in the reverse direction. It is in the rotatory motion means some torque is acting on the coil by itself. That the torque is nothing but restoring couple. When the restoring couple is produced in the absence of the external magnetic field. So the restoring couple produced in the loop. The restoring couple produced within the loop will be given by C into theta. Restoring couple which is produced within the rectangular loop will be given by C into theta, where theta is indicating what? Theta is indicating the angle rotated by the rectangular loop, and C is indicating what? Twist constant. C is indicating what? Twist constant. It is a constant value for a given material. Now, in the case of the equilibrium condition, so what is the mean by equilibrium condition? Net torque is equal to 0. In the equilibrium condition, net torque is equal to 0. If any one of the body was said to be in the linear equilibrium, net force is equal to 0. Here, the loop will be rotating, so that we consider which concept? Rotatory motion. So, in the rotational equilibrium, already we know that net torque acting on the system is equal to 0. Net torque acting on the system is equal to 0 means what? External torque is equal to restoring couple. So, net torque is equal to 0 means what? External torque. Suppose external torque will be acting in the anti-clockwise direction. This restoring couple will be acting in the clockwise direction. For understanding purpose, if we assume external torque will be rotating the coil in the anti-clockwise direction, the restoring couple will be rotating the same coil in the clockwise direction. So, in the equilibrium condition, what we will wrote? Net torque acting on the loop is equal to 0. Net torque acting on the loop is equal to 0 means what? External torque value is equal to restoring couple. So, what is the external torque value? BIAN. Restoring couple value is equal to what? C into theta. Now, see here. So, whenever the external torque value will be is equal to the restoring couple, we write that BIAN is equal to what? C into theta. Here, I will write the expression for the current. So, therefore, I is equal to C by ban into theta. I is equal to what we got the equation? I is equal to C by ban into theta, where C is called what? Twist constant. This is a constant value for the given material. Which metal we consider here? Phosphor bronze wire metal will be considered. For the phosphor bronze wire, C will be a constant value and B is the applied magnetic field. A is indicating the area of the loop, N is indicating what? Number of turns. So the entire term C by ban will be assuming as a quantity K. K is equal to C by ban. I am assuming that C by ban term will be is equal to what? K. Here K is called as galvanometer constant. So what is the K here? K is indicating what? Galvanometer constant. So if you substitute the K here in the place of C by ban, you will be getting that I is directly proportional to theta. I is directly proportional to what? Theta. So this is a required relation in the case of the moving coil galvanometer. So what is the required relation? I is directly proportional to theta. It is saying that whenever we are increasing the amount of the current, which is passing through the coil, it is also making so many number of revolutions. As the I value increases, theta value increases. Theta is about angle rotated by the loop. If I value will be small, the loop will be rotated by smaller angle. If I value will be more, the loop will be rotated by large amount of the angles. So this is about moving coil galvanometer. Next one, advantages of the moving coil galvanometer. The first one is, in generally, while we are doing the experiments regarding the magnets, suppose one deflection magnetometer will be there as well as tangent galvanometer. These two are different devices. We are using the magnetism. While you are doing either a tangent galvanometer experiment or deflection magnetometer experiment, those instruments must be aligned in the earth magnetic meridian. So what is the magnetic meridian means? We will discuss in the magnetism topic. That is the vertical plane which is passing through the earth north and south pole. That is called what? Magnetic meridian. So those devices called, which is a tangent galvanometer as well as deflection magnetometer, they will be arranged in the earth magnetic meridian. But coming to the moving coil galvanometer, while you are doing the moving coil galvanometer experiment, it is need not to arrange the given moving coil galvanometer in the earth magnetic meridian. So what is the first point? The moving coil galvanometer is need not to arrange in magnetic meridian. Need not to arrange in the magnetic meridian. Why we are not arrange this moving coil galvanometer in the magnetic meridian means, in generally, the earth magnetism is very small. The magnetic field intensity of the earth is what? Very small. But in the moving coil galvanometer, what we are using? We are using a high intensity magnetic field, which are produced by the horseshoe permanent magnets. So comparing to the magnetic field which we are using in the moving coil galvanometer, the magnetic field intensity of the earth will be very small. That's why we neglect the arrangement of the moving coil galvanometer in the magnetic meridian. Once again, why we did not align this moving coil galvanometer in the magnetic meridian means, the magnetic field intensity what we use in the case of the moving coil galvanometer is very much stronger than the earth magnetic field. So that it is need not to arrange the moving coil galvanometer in the magnetic meridian. So this is the first advantage of the moving coil galvanometer. Second one, we define galvanometer constant. What is the galvanometer constant? C by ban. So in this equation K is equal to C by ban, where B is indicating the magnetic field intensity which is produced by the permanent magnet. A is the area, N is the number of turns, C is the what? Twist constant. So this K value is also, independent of, K value is also independent of earth magnetic field, So in the galvanometer constant, what we write the formula K is equal to C by ban, that K function is also independent of earth magnetic field. It is depends upon the magnetic field which is produced by the permanent magnetic field which is produced by the permanent magnet. So that whatever the deflection we got, deflection produced in the moving coil galvanometer, is also independent of the deflection which is also produced in the case of the moving coil galvanometer, is also independent of the earth magnetic field. K is independent of the earth magnetic field as well as the deflection which was produced in the moving coil galvanometer is also what? Independent of the earth magnetic field. So this is the second advantage of the moving coil galvanometer. Next, in generally, while we are doing any one of the experiment regarding the magnetism, nearby that equipments, nearby the experimental devices, any magnetic materials are present, their readings will be changes. But in the case of the moving coil galvanometer, while you are doing the moving coil galvanometer experiment, if any other magnetic materials are present and surrounded by the moving coil galvanometer arrangement, the deflection does not be changes. The readings value does not be affected. Why again means? Already the same explanation. Why? Whatever the field produced within the moving coil galvanometer is a very intensive field. So the effect of those materials will be negligible with respect to the field what we assume in the case of the moving coil galvanometer. So the third point is what? The magnetic materials surrounded by the moving coil galvanometer, the magnetic materials which are surrounded by the moving coil galvanometer does not affect the deflection produced in the moving coil galvanometer. So while you are doing the experiment, if any magnetic materials are placed nearby the moving coil galvanometer, those are not affecting the results what we take by using the moving coil galvanometer. Next, in the moving coil galvanometer, you got the relation I is directly proportional to theta. You got the deflection, I is directly proportional to theta. So by using the moving coil galvanometer, whatever the readings you are measuring, whatever the current you are measuring, those values we have to measure more accurately. That means the readings we are taken in the moving coil galvanometers are having more accuracy. The readings what we calculate by using the moving coil galvanometer are having what? More accuracy. So it is also one of the advantages of the moving coil galvanometer. And the fifth one is the main purpose of the moving coil galvanometer. What is the main purpose of the moving coil galvanometer? By using the moving coil galvanometer, we are measuring the very small currents. What are the small currents range? 10 power minus 9 amperes. That means, in generally, if you use the ammeter, those devices, they will be measure the large currents only. But to measure the very small currents with more accuracy, to measure the very small currents with more accuracy, we are going to the device that is nothing but moving coil galvanometer. Moving coil galvanometer. So these are the advantages of the moving coil galvanometer. Advantages of the moving coil galvanometer. Next, disadvantages. Disadvantages. So here, in the case of the moving coil galvanometer, it is a device which can be used to measure a very small currents, That means the moving coil galvanometer is very sensitive. The moving coil galvanometer is what? Very sensitive. It is a device which can be used to measure very small current only. Suppose through the moving coil galvanometer, if a large current will be flows, then what will happen? The moving coil galvanometer will be getting damaged. So that this moving coil galvanometer is not suitable. The moving coil galvanometer is what? Not suitable for large currents. It is not suitable for what? Large currents. This is the main disadvantage of the moving coil galvanometer. So this is about advantages and disadvantages of the moving coil galvanometer. And one more last topic is there in this moving coil galvanometer, that is nothing but sensitivity. That is nothing but what? Sensitivity. Next one is what? Sensitivity of the moving coil galvanometer. Sensitivity of moving coil galvanometer. So generally when we will say a given device is a more sensitive. A given device is a what? More sensitive means for a small input. If the given device will be giving the standard outputs, standard results, then we will say that the given device is sensitive. Once again, see here. So when we will say a given device is more sensitive means whatever the device we use for that given device, for the small input, if the device will be producing a large amount of output, results, then we will say that the given device is more sensitive. In the case of the moving coil galvanometer, what the result you got? I is directly proportional to theta. I is directly proportional to what? Theta. What we said, if we increase the current value, the deflection produced within the galvanometer is also increases. So that here the current will be saying as input, and the deflection produced in the galvanometer, within the galvanometer will be saying as what? Output. So if you want to say that moving coil galvanometer will be more sensitive means for the small input current, if the deflection will be produced in the moving coil galvanometer will be more. If the deflection will be produced in the moving coil galvanometer will be more or large, then you said that the moving coil galvanometer will be more sensitive. So finally what we conclude, when the galvanometer will be more sensitive means if the moving coil galvanometer will be producing the large deflections for the small input current, such device is saying as a what? Sensitive moving coil galvanometer. Now here we are going to define two definitions. One is current sensitivity. First one is the word current sensitivity. So can we define the current sensitivity? The amount of the deflection which is produced in the rectangular current carrying loop per unit amount of current flows through it. Such type of So current sensitivity, how can we define the current sensitivity? Current sensitivity is the amount of the deflection produced within the coil per unit amount of current flows through it. So the current sensitivity is denoted by theta by I. Current sensitivity is denoted by theta by I. Already you know that I is equal to C by ban into theta. I is equal to what we know previously. I is equal to C by ban into theta. Here current sensitivity is defined as deflection produced per unit current. So theta by I. From that equation, theta by I is equal to ban by C. Current sensitivity formula is equal to what? Theta by I is equal to what? Ban by C. How can we define the current sensitivity? The amount of the deflection produced within the coil per unit current flows through it. That is called what? Current sensitivity. Next definition is voltage sensitivity. So how can we define the voltage sensitivity? In the case of the current sensitivity, you define that the deflection produced within the coil per unit current flows through it. So whereas in the case of the voltage sensitivity, it is defined as deflection produced within the loop per unit voltage applied across it. So therefore voltage sensitivity is equal to the amount of the deflection produced within the loop per unit voltage applied across it. So theta means theta only. According to the Ohm's law, can I write V is equal to IR? So here we consider the moving coil galvanometer. For the moving coil galvanometer, we are assuming that the resistance of the galvanometer is equal to capital G. So according to the Ohm's law, I will write V is equal to I into G. V is equal to what? I into G. Now 1 by G, this value is equal to what? Theta by I. 1 by G into what? Theta by I. Theta by I is nothing but what? Current sensitivity. So we will also write voltage sensitivity is equal to 1 by G into current sensitivity. This is one more relation between what? Voltage sensitivity as well as current sensitivity. So voltage sensitivity is equal to 1 by G into current sensitivity is equal to what you got? Ban by C. So voltage sensitivity formula is equal to what? 1 by G into ban by C. So this is about sensitivity of the galvanometer, current sensitivity as well as voltage sensitivity. Here one more point we have to discuss. In the moving coil galvanometer, we consider phosphor branch wire. Which wire we consider here? Phosphor branch wire. Why we consider this the phosphor branch wire? What is the advantage of the phosphor branch wire? This phosphor branch wire will be having high elasticity and low rigidity. Why we choose phosphor branch wire means the nature of the phosphor branch wire will be having what? It is having the high elasticity. That means its Young's modulus will be more. Its Young's modulus will be more. If the Young's modulus will be more, that wire will be more stiffer, more strong. So, for which purpose we are using the phosphor branch wire means that the phosphor branch wire will be having the property of high elasticity in nature as well as low rigidity in nature. Due to the high elastic nature, it will be very strong, and due to the low rigidity, it is easily twisted. It is what? Easily twisted. Because of that reason only, even for the small amount of the current, for the small amount of the current, the moving coil galvanometer will be giving the large deflections. What is the reason behind? The moving coil galvanometer will be giving the large deflection means this is the reason. The phosphor branch wire, what was used to connect the rectangular current carrying coil, will be having the low rigidity. Due to the low rigidity property, it is easily twisted. As a result, even for the small amount of the currents also, even for the small voltages also, the moving coil galvanometer will be producing the large deflections. That is the need of phosphor branch wire. This is about moving coil galvanometer. Thank you.